the point in radial basis function networks they're usually abbreviated as RBF networks, is that we want to use a different first layer. So we still want to use basis functions in the original parameter space, but they should be more spatially localized. And the way it works is that your prediction is given by some bias plus a number of parameters, and the summation is now over your weight functions. So M would be the number of weight functions. Wj is now a scalar this time, times, in analogy to what we saw before, let me call this Sj of x, and Sj of x is e to the minus x minus mu j, where mu j is the center of the jth basis function. Then the covariance functions are typically assumed to be isotropic, and the even the variances are often fixed in advance. So I'm not putting a parameter j here on the sigma. I'm assuming that the same has been used for all basis functions. There you go. And in this type of networks, the centers of the basis functions, the mu j, are fixed in advance. For instance, by some clustering algorithm, such as k-means, which we very briefly discussed a week ago, or 2 weeks ago. And then the only thing that needs to be learned are the B and the Wj. And if the mu j are fixed, then these are learned easily by solving a linear system of equations. Which you derive simply by minimizing the sum of squared residuals. So it's in essence a regression problem that you are solving here. Now, for the fun of it, we can bring this actually in the kind of funny graphical notation that we saw before for the perceptrons. I'm showing this for a single basis function only, and it doesn't make much sense. But I just want to show that it's possible in principle. So these are the original features, and you can then say that we have a perceptron a trivial perceptron that takes the first coordinate and subtracts the first element of the normal vector. And you have a trivial perceptron that takes your second coordinate and subtracts the second element of your mean vector, and each then has an activation function, which is the square, so the operation of squaring a number, and these can then be summed up in a new perceptron, which has a Gaussian activation function. And all of that would now be, so all of that would be your first output, let's say S1 of your first perceptron. So here these mean vectors, I give a subscript 1 to say it belongs to the first RBF, to the first radial basis function, and the second index means I'm talking about the first component. And all of this would give S1. And I can now replicate this entire structure to give me an S2. I'm not drawing it now, and I can replicate the structure again to give me an S3. So you can see that you can plot it as a kind of network as we did before, but the analogy, is a little superficial. And then at that point, you can multiply with these weights W1, W2, W3, and have a summation unit that takes as input your bias, and out comes your prediction, y hat of x. Okay, and I've omitted the replication of this complicated structure here. So that is a radial basis function network, and they were actually quite popular until the late 90s, when I think it was this paper that signaled the end of that epoch. You see, this was a joint work by proponents of support vector machines and by people who had been successfully working with radial basis function networks for a few years, and they worked together on the same data set. And of interest is the test performance here. I think it's some digit classification problem, and on the test set, the support vector machine with no tweaking whatsoever got a 4%. The RBF, where the centers were found by k-means clustering, found a 6.7%. And if you use the RBF centered on the support vectors of the support vector machine, which are not normally accessible, you get something which is still a little bit worse than the SVM. And it is the success in this kind of digit recognition and similar tasks. It is this kind of success in the support vector machines, plus their convexity and their sparsity, that made them such popular algorithms. And this is why you will finally learn about them when we meet again next week. And I have exactly 30 seconds to go. Let's take the questions offline, okay? Thanks very much.